Okay, so today in Energy 101, we're going to go over energy and power. All right, so these are kind of the questions we're going to answer today. That what's the difference between energy and power? How do I know how much energy is converted given power and time? And then the square and cubic units we've already gone over in previous lessons, so we won't worry about that one today. Okay, first of all, a review of a previous lesson. So what is energy? So from a sort of a physics definition, energy is the ability to do work. That's how physicists would define it. But some ways to think of it that we've talked about before, it causes things around us to happen. And I also remember we went over a lot that it's an amount of something. So like you have a certain amount of energy, right? So we had our few examples. We had, the wood versus, a toothpick versus a quart of wood, a gallon versus 100 gallons, and so forth. So just keep in mind that energy can be quantified and that we can have, different amounts of it, okay? And we can measure it and we can convert between units, right? So speaking of units, remember our basic English or American unit of energy is the BTU, which is the British thermal unit, which is the amount of energy it takes to heat up 1 pound of water, 1 degree Fahrenheit. Remember it's basically equivalent to if you had a wooden match and you burned it all the way down, that's about 1 BTU's worth of heat energy. Right, so we had a bunch of different unit conversions that I'll go over here in a second. So our different energy units, there are a lot of energy units. The really specific ones that we've gone over before, joule, kilowatt hour, BTU, and calorie. These all have very specific equivalencies. Whereas we have some of these other units that are sort of more practical units that we measure, an amount of energy, like if we're using natural gas, often it'll be measured in cubic feet, 100 cubic feet. Could be measured in therms as well. We have gallons of heating oil, gallons of gas, gallons of protein, right? So propane, excuse me. So there are a bunch of energy units out there. But the really important thing to remember is that you can convert any unit to any other unit, and you just need the conversion factor. Okay, so then we went over some conversion factors before. Here's the ones, the ones in bold are the ones we use more often than the others. So kilowatt hours equivalent to 3,412 BTUs, right? 100 cubic feet of natural gas. So the sort of other units, the practical units, they can vary, depending on the sort of the purity and the quality of the fuel source. Whereas these have very specific definitions up here. Okay, so we've gone over that before. I'm not going to go over that again. But it's really important to remember that as long as you can find a conversion factor, you can convert any unit into any other unit. Okay, so that's energy, right? So the ability to do work. So the question is, what is power? So power and energy are absolutely related. Okay, so power is the rate at which energy is converted. Okay, so power is a rate. Energy is just an amount. Okay, so you have a certain amount of something. All right, so energy is like I have this much energy, period, right? It's just an amount. Whereas power actually directly indicates that you're converting energy from one form to another. Okay, so if you just have some energy just sort of sitting there, whether it's a gallon of gas or whatever, you're not necessarily using any power unless you're actually converting the energy from one form to another. Okay, so the power tells you how quickly you're converting energy from one form to another. Okay, and it's measured in energy per unit time. Okay, so because it's a rate, it's energy per unit time. And so if you want to take a second and think about some things that you might have a power rating for, all the stuff that we had energy ratings for, we'll also have power ratings for, right? So a battery has a power output, the human body uses a certain amount of power, so over a given amount of time, it uses a certain amount of energy. We can calculate the power used by all the people on Earth. You could look at the power used by a furnace, in this case a gas furnace. Like how quickly does it burn through energy? How quickly does a light bulb convert electrical energy into light and heat? How much power does the sun spit out? How much power does Delaware Tech use? So all these things that if we can look at the amount of energy that something is using, if we know sort of how quickly it's converting energy from one form to another, then we can actually indicate how much power it's using. All right, so these are very much related. So remember that power is energy per unit time. It's the rate at which energy is converted. Okay, so let's look at an example or two here. So furnaces are rated in BTUs per hour. Okay, so What do you think that means? Probably pretty straightforward. So this is the number of BTUs of energy it burns through in an hour, okay? So why is this a power rating? So I want you to think back to our power, how we define power. Remember, it's energy per unit time, okay? So this is pretty straightforward, BTUs per hour. So BTU is energy, right? Hour, of course, is time. So that is power per unit, or excuse me, energy per unit time, okay? So it's a power rating. And just an FYI, this is, furnaces are rated in BTU per hour, like this old oil furnace. It just tells you how quickly it's burning through the fuel. It doesn't actually mean how much it's actually you're getting out of it. And because of inefficiencies, it's not going to actually spit out as much energy as it's burning through. Anyway, that's just kind of an aside that we'll go over in more detail later. All right. So if you think about it this way, if remember that power is energy per unit time, and if you want to start thinking about how much energy you're actually going to use in a furnace, okay, it's actually pretty straightforward. So if I'm going to, in this example, use 100,000 BTUs per hour for 10 hours, how many BTUs will I burn through? Okay, and all you have to do is multiply the two together. Okay, so energy, as it turns out, is power times time. So this is power times time in the basic, right? So you set this up and the hours cancel out with the hours and you're left with BTUs. So you have 1 million BTUs, okay? So energy is power times time. Okay, so electronics are rated in watts, right? So we have our incandescent here and a CFL. So watts is actually a power rating. This tends to be one of the most confusing things for people that are just getting into the energy field. So how is this a power rating? And it's a little bit difficult to think. Remember, power is energy per unit time. And I think one of the easier ways to remember this is that a watt is actually equal to a joule per second. So maybe that'll help. So a joule per second, if you think about energy, power, and time units here, what are we looking at? So a joule, remember from previous lesson, is the international unit of energy. A second, of course, is time. So it's energy per unit time, right? So that's actually power. So another way you might want to think about it, something that we've looked at a little bit before. So if I use 100 watt hours of energy in 1 hour, okay? So remember, we've gone over watt hours, we've calculated watt hours previously. So watt hours is one of our units of energy. If we use 100 watt hours in 1 hour, how many watts of power did you use? And I don't want you to get kind of bogged down in the conceptual side of this. I want you to think about the sort of mathematical, the quantitative side of this. So how would you set this up as a math problem? And all you have to do is you have 100 watts divided by 1 hour, right? So 100 watts divided by 1 hour, you cancel out the hours, and you end up with 100 watts, okay? So that's, remember, energy per unit time, and you end up with power. So this one, again, is pretty confusing, and throughout the semester, I will sort of hammer this home that watts are a measure of power, and watt hours and kilowatt hours are a measure of energy, okay? So just remember, maybe a joule per second, or you can think of it as a watt hour per hour. Either way, it's energy per unit time, energy per unit time, okay? So let's just go over a few things here. So in this chart, we have our units on the left-hand side, okay? And then I want you to just go ahead and press pause and think about, are these units of energy or are they units of power? Okay. So a joule is a unit of energy. That's our international unit. Watt, remember, is power. A kilowatt is power. Anything with a watt, okay? Kilowatt, megawatt, gigawatt, terawatt, you could go on and on. Anything that's a watt is actually power. So 25 watts is obviously power. 100 watts is obviously power. A BTU, remember, is our American unit of energy. And then a BTU per hour, excuse me, that's energy per unit time, so that's power. So in this column, you'll think, how many watts is this? Okay, so how many watts is this, are each of these? So some of these are pretty straightforward. So 1 watt is equal to 1 watt. Obviously, a kilowatt is 1,000 watts, right? And just like a kilowatt hour is 1,000 watt hours. 25 watts is obviously 25 watts. 100 watts is 100 watts. So we have this. Why do we have this joule and BTU is not equivalent to any amount of watts? So I want you to think about that for a second. Press pause if you want to. And the reason here is that you cannot convert one unit into another unit if they're different types. This would, trying to convert joules to watts or BTUs per watts. Remember, this is energy and power, energy and power. This would be like trying to convert, a distance to a velocity. Okay, you can't do it. Even, almost like converting, distance to time or something. It's just, you can't do it. There's no equivalency between the two. You have to add that time component in order to relate energy and power. Okay, and then, this is a little bit a little more complicated, but you can actually convert a BTU hour. BTU per hour is a power unit. We can convert it to watts if you want to. All right, so let's just do, we'll go over a couple more things here first before we do a few calculations. So a 25 watt CFL uses about 25% of the power of an incandescent. So these two light bulbs will spit out the same amount of light, okay? So this is an incandescent, uses about 100 watts. This is the CFL, uses about 25 watts. So what does this mean in terms of energy use, right? So remember, 25 watts and 100 watts. So these are two different power ratings. So I want you to think, okay, this is a power rating, and I can buy a light bulb and say, here's the power rating of that light bulb. But what does that actually mean for energy use? Like, what does it, what does it indicate for energy use? Let's say I put both of these in a light socket. What is the implication here? And the implication here is that the incandescent it's going to use energy at a faster rate. Okay. So another way to think of it, the incandescent is going to use about, for 1 hour, if I plug in this incandescent, I use it for 1 hour, it's going to use about 100 watt hours. How do I know that? Because 1 watt times 100 watts times 1 hour is 100 watt hours. Whereas the CFL you use about 20, right? So I have these two different power ratings. If I use it for the same amount of time, with the incandescent, I'm going to use 100 watt hours over the course of 1 hour. With a CFL, it's 25 watt hours over the course of 1 hour. Okay, so the key here is that these two light bulbs have a power rating. The only thing that tells you is that if you would actually use them for a certain amount of time, this one's going to use energy at a faster rate. So it's going to use more energy over the same period of time than this one. And it's just, it's a completely proportional. So if this is 4 times the power as this, it's going to use 4 times the energy over the same amount of time. If it's 10 times the power, it's going to use 10 times the amount of energy. Again, the key here to remember is this is a power rating, and all this tells you is how quickly it's going to go through energy, or really how quickly it's going to convert energy from one form to another. All right, but you have to know the time component to figure out how much energy it's actually using. So just to kind of hammer this home one last time, a unit of energy only tells you the amount. Okay, it doesn't tell you the rate, right? So you need to know the time component to know, how much power it's using. And here's an example. If I tell you I use about 10,000 kilowatt hours, okay, that only tells you how much energy I use. That's just an amount of energy, right? But if I said I used 10,000 kilowatt hours last month, that tells you how quickly I'm going through it, right? If I say, I burned 20 gallons of gas, what does that tell you? Well, that just tells you I used 20 gallons of gas. So if I say I burned 20 gallons of gas yesterday, right, that tells you how quickly I was burning through the gas. If I burned, I say I burned 20 gallons of gas last year, that also tells you rate. So the key here is that by just saying, well, I used 20 gallons of gas, all you know is the energy, right? So that's only energy. You have to add that time component to tell you, okay, how quickly am I actually converting that energy from one form to another? And so without knowing the time component, you do not know the power rate, okay? So power, it gives you the snapshot, okay? So it's the rate at which energy is being used, or the rate at which energy is being converted. So you can think of it, something that's using 100 watts is converting energy at a faster rate than something using 25 watts. If I have a furnace that's burning 100,000 BTUs per hour, it's just converting that energy at a faster rate than something at 50,000 BTUs per hour. And the thing to remember is that the whether or not you use more energy, it depends on how long you use it for. So all else being, if I use these two light bulbs for the same amount of time, I'm going to use more energy here. If I use this, these two furnaces for the same amount of time, I'm going to use more energy here. Okay? So I think this makes a little more sense once we start doing some calculations. It's kind of hard to sort of explain your way through it, but once you start doing calculations, it should make a little more sense. So, our two basic formulas. We have power is energy times time, and if you do a little algebraic rearrangement, you know that energy is power times time. These are really, really important. We'll be using these throughout the semester. Okay, so let's remember these two equations. So if I use a 100-watt lamp for 100 hours, how much energy did I use? Okay, so remember this is power and time, so energy is just power times time. Pretty straightforward. You set it up, 100 watts times 100 hours is 10,000, and then watts times hours is just watt hours. Okay, really easy. So remember, energy is power times time. Power times time, and that's my energy. All right, so if I have a 25-watt lamp for 100 hours, okay, so this is kind of the scenario that I mentioned before. You use these two light bulbs or these two lamps for the same amount of time. How much energy do I use? So see if you can set that up. Right, so 25 watts times 100 hours. So it's power times time is energy, right? And then you multiply it out, watts times hours is watt hours, and that's my answer. So you can see if I use these same two light bulbs or lamps of the same amount of time, I'm going to use 4 times as much energy with this one because it uses, converts energy at a faster rate. All right, pretty straightforward. Okay, so if I burn 10 CCFs an hour for 5 hours, how much energy do I use in both CCFs and Us? Okay, so remember, energy is power times. So this is my power rating, and this is my time. That's how I set it up. So CCFs per hour times 5 hours, right? The hours cancel out, and I'm left with 50 CCFs. So how do I convert this to BTUs? So think about our conversion factor here. And feel free to press pause and look it up. So our conversion factor is 103,000 BTUs per CCF. Oops, excuse me. The CCFs cancel out, and you end up with 5,150,000 BTUs. Okay, so remember, power times time. Power times time, you get energy, and then you can convert energy units to any other energy unit. Okay. All right. So how about for the same lamps? How much would that be in kilowatt hours, and how much would that cost if electricity costs 15 cents a kilowatt hour? And also, if I use that same furnace, 10 CCFs an hour for 5 hours, how much would it cost, assuming $1.50 per CCF? Okay, so first we have our, we determined the watt hours, for each of these lamps. So how do we convert 10,000 watt hours to kilowatt hours? Remember, our conversion factor here is 1,000 watt hours is 1 kilowatt hour, right? So we end up with 10 kilowatt hours here. And then we do the same conversion factor for this one, and we end up with 2.5. Again, same lamp, same amount of time, or different lamp, same amount of time. We use 4 times as much energy in kilowatt hours because it uses 4 times as much power. Okay, so let's think about how we figure out how much these would cost. Okay, assuming we have 15 cents per kilowatt hour, and I want you to treat it just like another conversion factor. So we have 10 kilowatt hours times 15 cents per kilowatt hour, 2.5 kilowatt hours times 15 cents, right? So the kilowatt hours cancel out, you're left with dollars. So it's $1.50 versus 37.5 cents, right? So this is set up just like any other unit conversion problem. Again, it costs 4 times as much to run something that's use 4 times as much power. Okay, so let's do this last one. If I burn 10 CCFs per hour for 5 hours, how much would it cost? All right, so first, remember we calculated that it uses 50 CCFs, and all you do is insert your conversion factor, right? So $1.50 per CCF. The CCFs cancel out, right? And you're left with dollars, and you end up with $75. Okay, so these are really basic calculations that we'll be doing a lot of this semester. We'll be applying a lot of different contexts, both sort of, doing labs like this and then also doing some measurements. And so in the lab this week, you'll get practice on calculating power using a bunch of different factors. Okay, and that's it for today's. Thank you.